Having to use first principles every single time is, well, a pain in the neck. It takes too long. So what we do in maths, of course, is look for patterns. That gives us a rule that we can just use for every time. So let's create some, starting from y equals constant. And yes, I know we know that one anyway, but let's prove it using first principles. If function x is equal to c, function x plus h would also be c. If we sub that into the formula, we'll get c minus c, which is 0. The limit as h approaches 0 would be 0, confirming what we already knew, that the gradient function or the derivative is 0 when y is equal to a constant. Let's make it a linear function then. And again, we already know the answer to this one because we know the slope of the line would be, in this case, it would be k, but function x would be kx, function x plus h, kx plus kh. Put it into the first principles formula, and we can cancel, confirms what we know. Okay, what about other powers then? X to the power of n. Remember, difference of two squares. A minus b, a plus b. And then there was difference of two cubes. And in fact, we said we could keep going. But the first factor would always be a minus b. The other factor would be a, and the powers would start going down by 1, and then b powers going up by 1. Why do I bring that up? Well, that's going to come in useful now for proving the derivative here. Function x is x to the power of n. So function x plus h would be x plus h to the power of n. So when I put that into the first principles formula, on the top of the fraction I have something to the power of n minus something to the power of n. We now know that factorises to b, well, a is x plus h, so x plus h, minus b, which is x. In the other parentheses then, the powers of x plus h are going down by 1, and the powers of x are going up by 1. But look at the first parenthesis, x plus h minus x, which is h. That'll cancel with the h in the bottom of the fraction. And I'm now left with this expression. But as h approaches 0, that's all going to become x to the power of n minus 1. The next one would be x to the power of n minus 2 times x, which is x to the power of n minus 1. In fact, every single one of those will become x to the power of n minus 1. And the question becomes, how many of them are there? Go back to our pattern again. When it was a squared minus b squared, there were 2 terms. When there was a cubed minus b cubed, there were 3 terms. A to the power of 4 minus b to the power of 4, there were 4 terms. So logically, a to the power of n minus b to the power of n, there must be n terms there. Well, that means we now have a formula for our gradient function. It's simply nx to the n minus 1. Yeah, let's do some examples. If they give us y equals 7, other than saying thank you very much for such an easy question, we'd go, the derivative is 0. 37x, we know that's going to be 37. But now we know how to do this one. X to the power of 10, well, we bring that power down, 10x to the power of 9. If we have more than one term, it's all right, we just do each piece individually. Remember what we're finding. We're finding how the y value is changing. And our y value is built with these 3 things added together. So the change would be how those 3 changes are together. So I just differentiate each bit. 3x squared gives me 6x, 6x gives me 6, 2 gives me 0. Well, I don't write the plus 0 down. Something like this. At this stage, I'm going to have to expand it out. I get 4x squared plus 4x plus 1. And differentiate that, I get 8x plus 4. Now we have another question. Bring this one up just to point out, read the question carefully. So easy to make a silly mistake here. They've said if function x is equal to x cubed minus 3, find the gradient function 2. And some people just quickly read it and go, oh yeah, I just substitute 2 in. No. It's not function 2 they're asking us to find, it's gradient function. Well, let's work out the gradient function. There it is, 3x squared. Substitute in 2 and we get 12. Let's go back to, I guess, where this all started. Let's find the equation of the tangent to this curve. It's a cubic. There is my curve. Find the gradient function. Again, that's just the formula that allows me to find the gradient. Now we substitute in the specific point, well, the x value. When x equals 1, we get 3. Okay, I know the slope I want is 3. I have a point. I have a slope, point slope formula, and I've written it in general form, but there it is. 3x minus y minus 2 is equal to 0. Find the points on the curve where the tangents are horizontal. Well, there's our curve. What's this question really saying? I want to know when the tangents are horizontal, when the gradient is horizontal, when the gradient function is equal to 0. Let's find it. dy dx is 3x squared minus 12. I want to know when they are equal to 0. Solve that. Plus or minus 2, but they've asked me for the points. They don't just want the x values. So let's sub that back in and we'll get the y values. Minus 2, 16 to minus 16. Just some terminology. We know about tangents, but there are these other lines called normals. And all a normal is a line perpendicular to the tangent at that point of contact. Here's a random curve. If that's the tangent, the normal comes through at 90 degrees at that same point. That's what we call a normal. So let's find the equation of a normal then. There's our function. The gradient function. That will tell us the gradient of the tangent. So I can find when x equals 3 that the tangent has a gradient of 21, but I want the normal. So I want the negative inverse. So the slope I want for this question is minus 1 on 21. Point slope formula. Ooh, horrible numbers. There we go. X plus 21y minus 612 is equal to 0. Just a note about setting out. Right? What are we actually doing when we're finding a derivative? It's still working on an equation. And that idea of what we do to one side, we do to the other, we're actually doing that. If I have y equals x squared plus 2x, we don't normally write this down. But what we're actually doing is this. We're differentiating both sides of this equation with respect to x. So actually, this is what I've got. I'm saying I'm going to differentiate y with respect to x. And then on the right hand side, I'm going to differentiate x squared plus 2x with respect to x. Now I've got a problem on the left hand side. How do I differentiate y with respect to x? They're different pronumerals. And the answer is we don't. We're going to end up with the answer dy dx equals 2x plus 2. But how did I get from differentiate y with respect to x to simply being dy dx? Because what we really did was this. I differentiated y with respect to y and then multiplied it by dy dx. Differentiate y with respect to y. Well, that's no different to differentiating x with respect to x. The answer is 1. Really, I've gone 1 times dy dx gives me dy dx. Now, obviously, we don't write those two middle lines down, but that's actually what we're doing when we're differentiating. You still, what you do to one side, you do to the other. But this idea actually is quite important, and we'll see that later when we look at implicit differentiation and things like that. But that idea is very important. The notation itself, in your setting out, match. So in other words, if they tell me y equals x squared plus 2x, then the notation I will use for the gradient function is dy dx. I match the notation. Or I suppose I could have used y dash. Now I've got to be honest, I very rarely use y dash myself. I would tend to go with dy dx. If they had written it as the gradient function, function x, then I would write the derivative as the gradient function, f dash x. Again, matching the notation they're using in the question. And if they simply said, hey, differentiate x squared plus 2x, then I would use this notation where I say, all right, I'm going to differentiate x squared plus 2x with respect to x. Matching the notation of what the question is asking that we're going to do. Oh, gone. Okay.